All right, so let's see if we can figure out what was up with that assembly example. We compiled some C code to assembly code, and the register naming was weird. To explain what's going on with that, I have to go back in time, decades, and talk about the history of sort of Intel family instruction set architectures, which includes the instruction set architecture that we're looking at, amd64. Now, the story begins in 1978. And in 1978, Intel released a microprocessor called the 8086. And that 8086 microprocessor was a 16-bit microprocessor. Now, we could go back a few years earlier and talk about a processor called the 4004 or another one called the 8008, which might have been a 8-bit microprocessor. But it's easier if we start off in 1978 with the 8086, because that was the processor that was in the original IBM PC, and it's also the processor that really starts to look reasonable. So when I say that this is a 16-bit microprocessor, what that means is a couple of things. But the most obvious thing that that means usually, and this may not apply concretely to specific processors, but in general, when we talk about a processor being 16-bit, that's the size of number that it likes to deal with, and also the size of the memory bus. So in a computer, we've got a processor, and that processor is hooked up to some memory. So this is the CPU, and this is the RAM, and these are connected together by some wires. So we have some data wires going over here, and if we have a 16-bit processor, that means we're going to have a 16-bit memory bus. That means that we're going to have 16 memory data wires, 16 data wires connecting the CPU to the RAM. So if the CPU is going to go ahead and request data from RAM, the RAM can send back a 16-bit number all at once in parallel down that bus. The CPU wants to write stuff to RAM, it can send a 16-bit number all at once in parallel down the bus. And another thing that tends to happen here is that addresses are going to be that size. So in order to tell the RAM where in RAM to write, or where the CPU wants to read from RAM, it also is going to require 16 bits to specify an address. So actually, if we're going to write a number, write 7, that 7 looks dumb. If we're going to write 7 from the CPU to RAM, what's likely to happen is the CPU is going to send a signal down an extra wire here, which is going to indicate that we're sending an address to write. And then what it's going to send down these 16 wires is the memory address, not the number 7, but where it wants to put the 7. And the RAM is somehow going to reply back or clock back on some other wire or something that it's ready for the data, or timing is going to say that it's ready for the data. And then we send the 7 down the wire, and then the RAM is going to, by timing or a response or something, say, okay, I've written that data. And so it'll take 2 messages down the bus in order to write something. That's possible. We also could have 16 data wires and 16 address wires. That's possible. But when we talk about 16-bit, one of the things that we're talking about is the size of numbers, and usually the size of an address that we're going to store in RAM there. Now, RAM is where we're going to store most of the data in our program, but if we want to operate on data, we don't operate on the data in RAM. Instead, we operate on the data in the CPU. In the CPU, there's some little places where we can store numbers called registers. And in the 8086, we had about 9 registers. And each register is able to store a single 16-bit number. Now, those registers have names. And if we want to add together 2 numbers in memory, what we're going to do is we're going to read a number from memory down the bus into a register. We'll read the second number from memory down the bus into a register. Then we do an instruction that adds the two numbers. That's going to put the result in a register. And then if we want to write the result back to memory, we will send the address and then the number down the bus to memory so we can write back to memory. But the CPU is doing the work, usually between registers. Although in Intel style systems, it frequently looks like we're operating directly on RAM just to be confusing. But simple model, operations happen on registers. So in this 8086, we have 9 registers, each 16-bit. So that means we can store either a number, which just represents whatever we want it to, or we can store a number, which represents a memory address. All right, so we have these 16-bit values. These 16-bit values can represent a memory address. So the 16-bit number, we can store a number between 0 and 2 to the 16 minus 1. That's the possible range of a number, and so that's the possible range of memory addresses. And in almost any modern computer, the thing that we're talking about with a memory address is 1 byte. So that means that the maximum number of bytes that we can distinguish with a 16-bit memory address is 2 to the 16 bytes. Now, 2 to the 16 is 65536. This number 65536 we sometimes call 64K. And that's because with power of 2 numbers, we get into the situation where 2 to the 10 is 1024. It's convenient to be able to have a power of 10 be a round number to talk about. And so we call 2 to the 10 1K. We call 2 to the 20 is 1 meg. And that ends up being a little bit more than a million, in the same way that 2 to the 10 is a little bit more than 1,000, 2 to the 20 is a little more than a billion, or sorry, a little more than a million, 2 to the 30 is 1 gig, a little more than a billion, 2 to the 40, a little more than a trillion, 2 to the 50, etc. But, so 2 to the 16, if we have a 16-bit memory bus, that means we can address 64K of RAM. I'm blurry. It's supposed to be autofocusing. That's fine. Maybe it's autofocusing on the board. All right, so we have these 9 registers, and the 9 registers are called AX, BX, AX, CX. This order is consistent. DX, BX, SI, DI, BP, SP. So that's 1, 2, 3, 4, 5, 6, 7, 8. So those are our 8 general purpose registers that we can sort of, as the programmer, decide what we're going to store in there. And then we have one more necessary register called IP, which is the instruction pointer. What the CPU actually does, its job that it spends all its time doing, is it's going to read instruction from address in IP. It's the first thing that it does. It's going to look in the IP register, and then it's going to request from memory one instruction at that address. It's then going to run that instruction. It's going to increment IP by 1 instruction, so however big the instruction is. On an Intel style system, instructions can be variable size, which is inconvenient. But then it's going to loop around and do it again. And it just does that forever. If we want to have it execute a different instruction, then the way we have it execute a different instruction is by changing the value of IP in the instruction. That's called a jump or a branch, and we sometimes do that. So this is our 16-bit processor. We have those 8 general purpose registers and 1 special purpose register. Because it's 16-bit, we can address up to 64K of RAM. Now, what sort of thing can we do with instructions? I'm gonna erase all this and then we'll find out. So we can do arithmetic. And an example arithmetic instruction might be add the number 5 to the CX register. In the assembly syntax that we're using, it's not clear that that's a 5. Let me try harder. $5 means that's the literal number 5. %CX means we're talking about the CX register. So what this instruction is going to do is it's going to read the value it's going to take the number currently in the C register, it's going to add 5 to it, and it's going to put the result back in the C register. We could specify our instructions in such a way that there were 3 arguments and the source and the destination were different. That's not how Intel style instructions work. We always are modifying a register. So there's 2 sources, one of which in this case could be a constant, it could be 2 registers, and then one of the sources is also the destination. Okay, we have test instructions. So we can compare 5 to the CX register. What that's going to do is it's going to do comparison operations. And in an Intel style processor, the way this works is kind of weird. What it does is it does every possible comparison, and then it's going to fill in a register called the flags register, which I didn't tell you about, special magic register called the flags register. And the flags register has a bit for every possible comparison. So this is going to set flags, and the flags bits are things like greater than, equal, is the result negative. There's a whole bunch of flags. You can go look them up. But as a result of it setting all these flags, we can then do conditional branch instructions. So we can say jump greater than or equal to and then give a target label where we want to jump to. And if the greater than or equal to, there's a greater than or equal to flag, there's a lot of them. If the greater than or equal to flag was set because of the compare instruction that is almost certainly on the previous line of code, so we always have a compare and then a conditional jump. So if the compare instruction set the GE flag, then we change the instruction pointer so that the next instruction we execute will be the instruction at the label. Otherwise, we just keep going. So this allows us to implement like if, while, for loops are all compare and jump. We have move, like mov. And we give a place that we want to move from and a destination that we want to move to. And when I say move, I really mean copy. So this could move from one register to another. It could move a constant value into a register. Or we can do something like this, where we have a register argument in parens. And what that means is we want to do a memory operation. So we're not going to move the value in the SP register to the DX register. What we're going to do is we're going to interpret the SP register as an address. Parens mean memory address. And then we're going to move the value in memory at that address into that register. We can put the parens on the other side. We can't have parens on both sides. That's a complication, but you can always have a temporary register that you can use to move things around. And that's the basic story. All right, so that's what we're doing with assembly. If we were in 1980, working with an 8086. In fact, if we were in 1986, we might still be working with the 8086 because processors were a little bit developed slowly at that point. But that was 16-bit. Let's move forward to the future. Forward to the past. Because the next part of this story is the 80386. Intel released the 80386 which we call the 386 in I don't have a date. Let me call it 1988. And it had a 32-bit processor. Now that means it had 32-bit registers, it had 32-bit memory addresses, and with a 32-bit memory address, how much memory could we have? What was the maximum amount of memory that we can address with a 32-bit memory address? You can answer this before I show you. So, maximum is 2 to the 32 bytes. And 2 to the 32, well, 2 to the 10 was K, 2 to the 20 was meg, so 2 to the 30 is gig. We have 2 left over. 2 to the 2 is 4. So we know we have a maximum of 4 gigabytes of address space. Maximum addressable memory. You couldn't have more than 4 gigs in a 386. And for a 386, as released in the late 80s, that was fine. The first ones came with like 2 megs of RAM. So 4 gigs was plenty. 4 gigs later became a problem, but we're not quite there yet. Now, in order to make this work, we had 32-bit registers. But Intel wanted to make it so that assembly code for the Intel 8086 would be able to run largely unmodified on this machine. And so we had 16-bit registers like DX, and the way the 386 was designed is they added new names for the registers. So we have extended DX, which is the 32-bit version of the 16-bit register. They're actually the same register. So if we have our DX register here, then the whole thing, so this is 16-bit, this is 16-bit, the whole thing is called EDX. And so you could store a value in EDX and then get the bottom 16 bits of that value by reading out of DX. You could store a value in DX and then read out of EDX, and maybe you get a weird result because you don't know what's in the top 16 bits, but that's how that works. Now, it's even more fun. If we go back a little further, there were actually more than one name for DX already. So we have DX is 16 bits, and this is true for all the other registers too. This could be SI and ESI. That's the 16-bit version, that's the 32-bit version. But if we look at DX, we have 2 8-bit parts. So the top half, the high bits, are called DH, and the low bits are called DL. So even in the 32-bit version of this instruction set architecture, different pieces of the registers have different names, and we can end up with 4 different names for the same register. This turns out to be useful if you want to, for example, convert a 32-bit number into a 16-bit number. You can just write into EDX, read out of DX, and what you get is a conversion based on just chopping off the top bits, which might be the behavior that you want, or more relevantly, if you know that is the behavior, you can write your program to take advantage of that behavior and have your program work as expected, because that's what you expect. All right, so that gets us to a 32-bit processor, and this was the standard IBM PC style computer processor from like 1990 through 2006. So then, there's of course another step, because 4 gigs of RAM isn't enough. That's sort of the key problem here, is that we need more than 4 gigs of RAM. So in 2002, 2004, AMD releases the amd64. And specifically, the thing that they released was the AMD Athlon 64 microprocessor. That was the processor that was the first AMD64 processor. Now, why didn't Intel do it? Well, Intel had a better plan. Their plan was that they were going to get rid of this clunky old architecture that they had built in the 70s, in the early 70s, this thing was backwards compatible to, and they were going to do a new processor from scratch using a new technology called very long instruction word, which looks really great in a lab. So they released a processor architecture called Itanium, which first came out for big servers and sort of supercomputer-y, mainframe-y sort of applications. And Hewlett-Packard bought a lot of it. They thought it was the greatest thing ever for their business customers, and nobody else bought any of it. Everybody said it won't run, it isn't backwards compatible with 386, so we can't even run Windows on it. What good is it? We definitely can't run any existing applications. So the Intel Itanium processor architecture was what they were pushing in the early 2000s, but nobody wanted it. AMD realized that they had this problem. They needed to go from 32-bit to 64-bit so they could have more than 2 or 4 gigs of RAM. It's not clear like where the cutoff is where things start to break. It's one of those. But they wanted to ship machines with like 32 gigs of RAM for servers, and they wanted to ship desktops with 8 gigs of RAM. And so to do that, they really needed a 64-bit processor. So they looked back in history at what Intel had done when they needed to go from 16 to 32, and they said, we're just going to do that again. We saw what you did, we can do it again, so we're going to go ahead and say that we're going to be a 64-bit processor. Now, their 64-bit processor had a 48-bit hardware data bus when they shipped it, which changes some of the numbers a little bit. I'll go through and talk about that, but from a software perspective, this is fully a 64-bit processor. It's only in hardware that it is largely limited to 48 bits in 2003. Nowadays, it's not limited to 48 bits anymore, but 64-bit processor with a 48-bit data bus is what the Athlon 64 was. So that means we have new registers. So if we have the DL registers is 8 bits, the DX is 16, the EDX is 32, so this was I think there may have been a historical machine where the 8-bit version was just called D, and so I really want DX to stand for extended to 16-bit, and then 32 is the extended register. I don't know where AMD came up with this, but we have like the really extended register, which is the 64-bit version. But we have one more name for the register that is a wider version of it. The registers are actually 64-bit in hardware, and then the names for the smaller pieces are just accessing the smaller pieces of them. Now that's one thing that they did. Another thing that they did is they added more registers. So they had a problem historically with there are 8 general purpose registers. For various reasons, you can really only use 6 of them on 386 because the stack pointer and base pointer register, we'll talk about what that means later. Stack pointer or base pointer registers have functionality in programs normally. So as the programmer, you really only have the 6 A, B, C, D, SI, DI registers to work with. And so that's not enough. You can get better performance if you have a few more registers. So we have extended registers, and then we have all new registers. And the all new registers that AMD introduced, because they didn't think that Intel's naming convention made any sense at all, they decided that their new registers are going to be called R8, R9, through R15. So that brings us from 8 general purpose registers, of which you can use 6, to 16 general purpose registers, of which you can generally use 15 for technical reasons. We're only going to be able to easily use 14 because we're going to follow the old convention because it makes sense. But in any case, with amd64, we go up to more than 10 registers from being like at 6 before, which is convenient for programmers. And especially convenient for compiler writers. It lets you optimize much better. All right, so how much RAM can we access with a 48-bit physical memory bus? So 10 is K, meg, 30 is gig, 40 is terabyte, 8 is, 2 to the 8 is 256. So this is 48 bits, gives a maximum address space of 256 terabytes. So a Athlon 64 processor in hardware, because of the wires, can't possibly have more than 256 terabytes of RAM. You couldn't have bought that much RAM for one anyway. And if you think about it now, how many people in this class do you think have a machine where not being able to have more than 256 terabytes is a problem? Maybe someone's worked at some ridiculous like big server cluster situation, but for most people, especially for sort of boring uses, 256 terabytes is still fine. It's not fine for large cases nowadays. It turns out that Intel is shipping processors with more now. But the limit in software was 64 bits. So T is terabytes, and I want to say that it goes terabyte, exabyte would be 50. Wait, no, terabyte, petabyte, exabyte. So 64 is going to be 2 to the 4 is 16 exabytes of RAM is the maximum that the sort of software design can support, and that's still fine. Most of the time, or sorry, on computers that people are actually building and thinking about putting RAM in, having the 64-bit address space limit isn't a problem yet. People, when they designed the 32-bit system and saw 4 gigs as the maximum, thought that would never be a problem. I'm not going to say this will never be a problem, but I'm going to go ahead and say that you'll have graduated from college before it's a problem. Okay, so that is the sort of story of where the registers came up, where the registers that we have and where the architecture that we are talking about came from. The problem that we saw in that program, the add1 program that we assembled, was that in the main program, it was moving a value to EBX, moving a program to EDI, and then in the function that it was calling, it was trying to pull the same number out of RDI, and the question was, why does that work? And the answer is because it's the same register, and the compiler just has to know for a fact that the high bits in RDI were zeroed before doing this, and then it's all fine. All right, so that's the story of that, and I think the next thing is we want to do a quick example.